in this video we're going to look at this theorem. So maybe you might want to press pause and have a quick read of this. It's saying that if you have a sequence, and you want to sum up all the terms from capital N all the way to infinity. So capital N could be here, it could be here, it could be anywhere. Let's just say capital N is here. If you want to sum up all the terms from capital N all the way to infinity, from capital N all the way to infinity, what you do is you map a function. So you map a function on top of your sequence. So you map a function on top of your sequence. So let's call this f of n. So you map a function on top of your sequence. So if you want to know whether or not this will converge or if this will diverge, what you do is you look at the area underneath the function. You look at the area underneath the function. You look at the area underneath the function. If this area converge, then the sequence, then the series itself will also converge. If this area here diverge, then this series will also diverge. So what it's saying is that these two, they act on par with each other. Either they're both converge or they both diverge. So it gives us another way of determining whether or not this will converge or this will diverge by looking at this. Okay, so now we're going to prove it. So we are trying to investigate this from the first term all the way to infinity. From the first term all the way to infinity. But rather than looking at it all the way to infinity, we are going to investigate from the first term all the way to n, to some arbitrary nth term. And then later on we can take the limit as capital N tends to infinity. The minute we take the limit as capital N tends to infinity, this thing here from 1 to n then becomes from 1 to infinity. So this is what we're trying to investigate. But in order to do it, we are just going to look at it. Later on, we will take the limit as capital N tends to infinity. So let's just look at it from the first term to the nth term. So we would use Riemann's upper sum to simulate this thing here. So if you look at this here, when x is 1, you put it into here, that will then jump to here, and then you times a width of 1. So this area here, A1. So this, by using Riemann's upper sum, this area here would represent our first term. When it's 2, you put it into here. This area here will be A2. So this area here can represent this, and this is A3. A3 can represent this, and then the very last term. Remember, up to n. The very last term, this area here will be an minus 1. So this would represent this. So by using Riemann's upper sum, we can only represent the first n minus 1 terms. We are actually missing this a capital N. So hang on. So using Riemann's upper sum, this area here would represent this. This area would represent this. This area would represent this, and so on. And the very last term, the very last rectangle would represent this. So now we say that the area of all the rectangles must be bigger, because we're using Riemann's upper sum. Must be bigger. The area, all the rectangles must be bigger or equal to the area underneath the function. So this is our function here. So the area underneath from 1 to n, from 1. So basically, using Riemann's upper sum, this thing here must be bigger or equal to the area underneath the function here. Must be bigger than this area here. So this area here represents this from 1 to n. Okay, but the thing is, we are trying to obtain this partial series up to n, but using Riemann's upper sum, we are missing this an, because this represents this, this represents this, this represents this. The last rectangle represents this. We're missing an. So in order to obtain an, So currently we've got this thing greater or equal to this thing. What we do is we add an to both sides. An to this side, and then if you add an to this on the right hand side, that's the same as you taking the integral from 1 to n plus 1. So the next term here would be an plus 1. So you can just so you adding an on this side here is the same as you taking the integral from here all the way to n plus 1. So all the way from 1 all the way to all the way to n plus 1. So because we are trying to get this thing here from 1 all the way to n, but using limits up the side, it only gives us up to n minus 1. So here we would add an to both sides. We would have this extra rectangle here. So this extra rectangle here is us adding this bit here. And then, but then on the right hand side, let's integrate it from 1, instead of integrating it from 1 to n, let's integrate it from 1 to n plus 1. So that's this bit here. So now we've got our whole partial series here. So this is from 1 to n. So now we've got from 1 to n now, and that's greater than this thing here. This thing here being from 1 to n plus 1, from 1 all the way to n plus 1. I will continue in the next video. So we established that from 1 to n, it will be greater or equal to the area underneath here from 1 to n plus 1 to n plus 1. But I will continue in the next video.